Welcome to the internal combustion boundary layer turbine engine, ICBLTE. This machine is a derivative of the Tesla turbine, which operates with flat disc. My name is Daniel Woody. I'm the inventor of this machine, and the presentation that you're about to see serves as an introduction, technology review, and business plan. Notes are available for each slide. If you right-click on the slide, you'll open a window that will show you the contents of the notes. The slides and notes can be printed as a handout package. Contact me at the web address for questions or comments. All bullets are explained in documents on the CSD, that's the Control System Development website. Dr. Nikola Tesla, originator of 300 or more patents and hugely responsible for the nature of our industrial world, provided patents which are in use every day in our modern world by billions of people. Amongst his discoveries are AC electrical generation, distribution, and the induction motor at the end of the distribution line for usage. His were also tuned circuits that made radio and TV possible, X-ray and fluorescent lighting, explored by him years before others went on to claim them as their own. The Tesla turbine, naturally, and the Tesla turbine, which is an external combustion or steam-driven engine, shares the same humble origins as the piston-driven engines, which is our internal combustion standard bearer today. So before you scoff, consider that coal, oil, and nuclear power plants are also external combustion systems. The top row of the slide demonstrates Tesla turbine with 20 9 3/4 inch discs producing 110 horsepower at its maximum efficiency, with the capability of generating 2 to 3 times as much horsepower. The bottom row is an example of a Tesla pump currently being produced and sold. Engines and pumps operate by virtue of viscous adhesion to the disc surfaces. The Tesla turbines are simple, powerful, and scalable due to the lack of complicating internal components. If you take a look at the simplified schematics on the right-hand side of both the top and the bottom row, you will notice how narrow the machine is, or the engine is, and the pump is also narrow in that fashion. The Tesla turbine and the ICBLTE are both relatively low torque engines. Power, however, is the product of high speed and torque. Both of these engines operate on the principle of fluid drag. The drag character that we are most interested in is the lateral or parallel adherence, with the other two drag characteristics being minimized. Fluid adherence to the surface of smooth disc are bound to those discs either by the boundary layering, and that boundary layering is relatively thick for liquids and relatively thin for gases. This NASA diagram demonstrates the concept of slip within the boundary layer that causes a drag on the surface of an object. The unsteady flow or the turbulent flow within the boundary layer causes the drag upon the surface of the object to diminish even to zero. This slide demonstrates the laminar flow around an object in a free stream, and how the laminar flow of fluid tends to adhere to the surfaces of the object around which it's flowing and impose a drag. The ICBLTE may be constructed with single or modular chassis design. The main stage, however, is necessary in any design, as the main stage supports the intake, compression, ignition, combustion, and exhaust, or the power output of the engine. The engine is a continuous, smooth burn operation, and can operate with any type of fuel, gaseous, liquid, or particulate. This slide demonstrates the schematic of a single chassis ICBLTE. This drawing is not to scale, but is meant to demonstrate the working fluid flow through the engine. The working fluid flow follows a path of least resistance due to the configuration of the differentially sized disc. This slide describes the enumerated operations of the ICBLTE shown in the previous slide. Here we demonstrate the pumping action of the disc. Pumping action is always present as long as the disc assembly is turning, and has to be overcome by the combustion pressure in order to achieve motoring action. Here we demonstrate the motoring action of the ICBLTE. The motoring action is the phase of engine operation where the combustion gases are converted to kinetic energy, and that kinetic energy is delivered to the central shaft output of the engine. The combustion gases flow in a vortex fashion while they are adhered to the smooth surface of the disc, and it is the spiraling in of those combustion gases that deliver energy by virtue of the conservation of angular momentum. This is a schematic of a modular or compound ICBLTE. It is not to scale, and it shows the auxiliary compression stage on the left, the main stage, and the auxiliary exhaust stage on the right. Again, this drawing emphasizes working fluid, or the path of least resistance flow through the engine. The modular design is flexible for changing application requirements. The ICBLTE will be able to replace all contemporary internal combustion engines due to its simplicity and its phenomenal power output. It will even be able to bring into existence new applications because of its scalability and its great efficiency. The main advantages of the ICBLTE as compared to piston-driven engines is its size, its scalability, its efficiency, and its power output. The ICBLTE is currently in the development stage for prototyping. Funding is required. There are three concepts of funding involvement shown under the prototyping stage. Any one of them is overlapping or indeed replaceable by the other. Manufacturing is shown, although there is no demand for manufacturing as yet, as a concept or as an example to illustrate the cost impact of an engine of this simplicity. All of these items are elaborated upon in the ICBLTE business plan found on page 5 of my website. As an example, I've chosen the automotive application for the ICBLTE. At 50 horsepower, this is enough for driving passenger cars in the city or down the highway. The associated battery pack can supply up to 300 horsepower or more for uphill or passing and can store energy accumulated on downhill or braking. The ICBLTE has outstanding performance when configured as a hybrid electric power plant. The first investors will enjoy the greatest profits in manufacturing and patent sharing rights. Risk has its rewards. Later investors will only partake in phenomenal rewards, where licensing will be available on a per application basis. Every application will require development tailoring. The Tesla turbine engine has run successfully in the past in both the external and internal combustion configurations. It's taken 100 years for contemporary turbine and reciprocating engines to reach the power and efficiency levels that the ICBLTE is starting at. The ICBLTE offers simplicity, long life, power, and efficiency, producing a smaller carbon footprint than its contemporaries. Control system development considers partnering with social entrepreneurship organizations to be a most desirable collaboration forward. This engine is the solution for today's internal combustion dilemmas. That concludes this slide presentation. Thank you for your attention and your time.